Hello, everybody. Thank you for being here. So, the purpose of today's session is to talk about how we can address a kind of hot topic when it comes to generative AI, and more specifically, the implementation of a RAG application. Perhaps I'm making a guess here, but how many of you know what is a RAG system? Okay, yes. So you are at the right place. Okay. So I have been working in IT during 26 years, and at DataStax for the last years more. And during this stay at DataStax, I have been working, first of all, in the NoSQL space. And the reason I am talking about that is because perhaps you don't know DataStax, but in reality you do. We already met. Because DataStax is the force behind Apache Cassandra, the popular NoSQL database, which supports a lot of strong critical use cases in the industry, especially with the main blockbusters like Netflix, Starbucks, and so. So what happened is we pivoting to the Gen AI market last year, and especially trying to find ways of helping enterprises to deal with the RAG pattern. So, but before starting, let's align on what is RAG. It will be quick. So, on this diagram, what you see, it's a way of taking the power of an LLM and take that power to effectively use it on our own set of data in the enterprises. The point is, the LLMs, how strong they are, have been trained on public data sets, and if we want to leverage them with our set of data, we need to pass on some context. Find a clever way of providing this data set to the LLM. So for doing that, we need to deal with a lot of mechanisms, but how smart this approach can be, we are going certainly to deal with something you already know. The challenge. The big one. And this challenge is called hallucination. So, as you can see on the screen, perhaps you may have the feeling that this image is moving. But it's not. It's an hallucination. So, the way it translates to RAG and generative AI terminology is the fact that when we get an answer back from the LLM, we think that we have a correct result. It looks like if we were having something absolutely accurate. The wording, the phrasing, everything, but it's not. And this is something difficult to understand, because when we are doing RAG, we still have enriched what we wanted to do with our own data set. And one of the goals of the RAG mechanism is to deal with this hallucination. We want to kill hallucinations out of this picture. But the bad news is LLMs are meant to hallucinate. Whatever we can do, they are going to still continue to hallucinate. This is by design. And on the screen, you see a kind of a study made on the 10th of September this year that demonstrates why and how, by design, LLM are going to still hallucinate. So that's kind of very difficult news, because as ML engineers, how can we deal with that? Well, normally, facing the hallucination issue, we should have tried something more than the naive RAG approach, meaning implementing advanced RAG techniques, There are a lot of them, a lot. And I count few of them, and if you don't use the ones on the screen, you will probably use 39 other of the others, period. So we have an inflation of techniques to try to manage this bloody hallucination challenge. And if you are not going to, you are going to use this one, but you are going also probably to play with other things, intelligent fine-tuning. And that's something that has been a kind of a push away for a long time, but now it's coming back again to combine the fine-tuning along with the RAG mechanism. And you can do smart things like memory tuning, and also trying to enhance everything regarding the prompt engineering to try to make a kind of prompt engineering free of hallucination. That's still a challenge, but some toolings are arising on the market. But you would still have to face hallucinations. But so far, you are talking about LLMs, about dataset, about techniques, but we haven't yet spoken about components. And among these components, there is one which is a key to face the hallucination and to fight against the hallucination issue, which is, in fact, the vector database. And what is kind of weird is that by choosing the correct vector store, you can directly win and gain 20% accuracy on your RAG pattern. Wow. So what does it mean? It means that the vector database component is not a commodity. It means that not all the vector databases on the market right now are not equal. And you need to be very precise in the way you are going to choose this vector store, because it will change the way and the success of your generative AI application. Also, something to bear in mind is it's very hard to go from the algorithm and the concepts to implementation. On paper, on PowerPoint, everything works. Easy. Yeah, you have an issue on the context because you don't provide enough context to the LLM. OK, play with Colbert V2 and it will be done. OK, fair enough. How do you do? How do you process what Colbert V2 implies? And on that specific point, most of the vector database fail. And finally, the generative AI works on a paradigm of similarity search. So it's like if, through similarity search, you can resolve all the needs you may have. No, it doesn't work this way. So, of course, dealing with similarity search is key, but it comes with some limitations. And the idea is, how can we deal with that limitations without having to add another database, buy new licenses, make more complex our DevOps, and so on. So that's very complex. So is there a way of providing data ubiquity from the vector store we are using, so we can use similarity search along with a graph approach to improve the accuracy? Perhaps there is an answer, but before answering to this answer, perhaps you can ask to yourself, OK, DataStax, fair enough, but are you legit in talking about this topic? Because you are perhaps well known for being the force behind Cassandra, but so far, till last year, you were just a NoSQL store, which is right, yeah. But in reality, when you are dealing with Gen AI pattern and problematics, you're dealing with exactly the same core concepts than you deal with NoSQL standards, meaning low latency, high data volume, always on access to the data, and linear scalabilities. And this is why, in fact, by layering down all the tooling and being able to orchestrate from deployments to services to APIs, we're able to serve a lot of enterprises use case at scale. So we are not the new kids on the block in terms of AI type of approach. And that means that we have been able to partner with all the hyperscalers, and we are nowadays integrated with all their framework, from Bedrock to Vertex AI and so on. So yes, DataStax as a kind of Gen AI authority built upon 14 years of serving the most critical data use cases in the planet, and already committed to help companies for AI projects. So what do we do specifically that beyond the NoSQL expertise we have a strong advantage when it comes to Gen AI? Well, in reality, when we look at the vector store, the main question is not about vector. We need to slice a little bit the issue and say that the big point is about the vector indexing. And this problem is known. From 2019, Microsoft discovered already that for Gen AI, the main concerns will be the way of using the full stack of components in an infrastructure to be able to serve efficiently what it means in terms of latency, performance, and so on, to serve accuracy. And at that time, Microsoft thought about a solution, partially, and the next point they didn't solve, DataStax solved it. So what did we do? Well, we look at what the industry has implemented as the main way of indexing the vectors, which is called HSNW. And this way of index layers the index in many layers, and the top layers are about having everything in memory. But as you can see on the slide, the layer 0 is the one who has the most context. The issue is that most of the time, database is waiting the vector to be read from the disk and not from the memory. And because you are reading for the memory, you don't have all the context required to provide a good context to the LLM. Hence, you have a bad accuracy. So another issue is about concurrency. Because when you index a vector, of course, on a batch type of approach, on a small data set and so on, that's very easy, very easy. But now consider the enterprise considerations in terms of real time, in terms of data volume, in terms of concurrency. I ingest, I embed, I store the embeddings, I index the embed, and while I'm doing that, I'm reading the embedding to serve my LLM requests. If you are in a sequential approach, imagine what is going to happen in terms of user experience, in terms of timeout to manage, and so on. That's the start of a nightmare. So HSNW, it's working sequentially. So first it indexes, and then it allows you to have the queries back. So we solve that with an index called gvector, which is based on a disk-INN implementation from the work from Microsoft we have been looking at. And what the index is doing is shrinking, it's a graph structure, So rather than having to deep dive into all the full structure of the index on all the layers, because it knows how to product quantize the information, you can index without having a loss of information. And because it's a graph structure, it can deep dive into it, and without having to go deep, it can retrieve the correct information. This way, you can have a better accuracy. The other aspect of it is that it is multi-threaded. So in other words, you can ingest, embed, index, and read the queries. So you don't have the sequential issue anymore. So you are solving and dealing with two types of main concerns in terms of concurrency. OK, what does it mean in terms of results? Well, if you take many types of data sets, and the reading and indexing time from Pinecone here, each time, and you see the one for indexing and reading the information with our technology based on G-vector, you see already the difference. You have a factor of 12. 12. But OK, will you say, what if I gain in performance, in latency, but if I am losing accuracy? I mean, nothing in Gen AI. We cannot sacrifice performance for accuracy. And this is what the DSKNN deal with. So we are optimizing the reads on disks, and we compare. We have very big and high performances. So in a nutshell, and to recap, by using a G-vector-based vector store, you will de facto improve your accuracy, your F1 relevance score, by 20% on average. And also, you are going to have 64 faster way of getting back your queries. Kind of nice stuff, no? And then you will have the ability to deal with demanding concepts. Meaning from that, if you want to implement Colbert's V2, for instance, which allows you to deal with very specific use cases where you need to find and ways of pushing high context by creating new dimension on each chunks, if you don't have the proper intersection methodology, you will never be able to get Colbert V2 working. Let me go quick here to say, as an example, if you embed with OpenAI embedding model, the space it will take on disk will be for a 10 million data set, 60 gigs of space. If you go to Colbert, you will have 12 times the amount, which means that you will have a degradation over time as soon as you are going to index, and you will have issues managing the memory. So that's why when you have an index that can deal by dealing with his memory management for you as G-vector, you will win in terms of accuracy. And you will be able to pass effective, large context to an LLM without having to change anything on your data set. And then we have this data ubiquity, meaning the ability to fill the gap with everything that similarity search does not handle. And by adding graph store, we are not doing classical knowledge approach, knowledge graph implementation. Because if you want to use a knowledge graph to implement on RAG, then you will have to ask an LLM to generate the graph for you. You will have to have a dedicated database, a graph one. You will have to use a specific LLM pattern to generate the cipher, to generate the links between the node and the edges. And you will need to model that upfront, meaning you know already what you are looking for, which is the opposite paradigm and philosophy we have in generative AI. That's undeterministic, and what we want is that freedom for the users. For example, here, when you have situation where some queries are far away in the hyperspace compared to the documents which are embedded, we have an issue. How do you want to find a similarity? No way. This is where moving from knowledge graph to entity-centric graph means that we can modelize the graph without having the need of a graph database. And then we will be able to use the graph paradigm to move from entity-centric graph to content-centric graph. So rather than purely indexing the document, we are going to index the chunks and make the graph from the chunks. So more powerful. Perhaps a demo will help you understand what I mean here. So on the graph here, I am using Langflow. Langflow is a tool that allows to fast-track the GenAI development and ease the pain by drag and dropping some components to effectively, with low code and no code, build something very powerful. So on the lane below, I have ingested in my vector store here AstraDB, which is a managed database in the cloud DataStax provides. Some URL on the documentation of DataStax. Believe me, it's it. OK? Here, you see some documentation. And I'm going to generate a graph without having a graph through that and store this information in my AstraDB database. And on the lane above, I am going to design my RAG pipeline. So I will have an input, which is a question of the user. I am going to embed my query, look for the context in my database, pass it to a prompt, pass it as a context to an LLM, and get back the question, the answer, sorry. And for that, I am going to use the classical similarity approach, asking the basic question about what are the index mechanisms we have in AstraDB. I can see in a WYSIWYG motion what I have been asking on my tool. And a few seconds after, streaming is not yet enabled in this pipeline. I will have an answer, which is accurate, but perhaps not enough precise. OK? So as you can see, we have information about G-vector, about the underlying index, and the summary. But now, without changing anything in my embedding, in my dataset, in my LLM parameters, just by changing the way I am going to look at the content-centric approach of my RAG, meaning by changing the similarity to traversal for graph, and relaunching the pipeline, we should see a difference in the degree of details, the quality of the answer we get back from the LLM. In other words, we have improved the context without having changing anything to the pipeline, except the way of extracting the context. And here, as you can see, I have a far more detailed answer on what is G-vector, far more useful, okay? Which means that by the fact, accuracy has been largely improved. So, in a nutshell, thinking about how you must choose the component vector store is a strategic decision. It will ease the development, secure and make so much powerful your user experience because you are going to solve, partially with that, among many other things you will have to implement, the accuracy challenge. So I hope this session would have been of interest for you. If you have any questions, we have a booth at DataStax, so we will be more than happy to answer your questions on the booth. So I would like to thank you for your attention. Have a nice conference.